Hey guys, have you ever turned off a circuit breaker and measured the voltage just to be sure it was off, expecting to see zero, but instead seeing 5, 10, 15, or even 30 or 40 volts? If so, you may have seen what some electricians call a phantom or ghost voltage. They call it that because they believe that somehow it really isn't there. Electricians only care about voltage that can cause electrical arcing, possibly start a fire, or voltages that are capable of supplying significant power or electrical shock. If it doesn't do any of those things, then as far as they're concerned, it isn't something to worry about. So they just call it a ghost or a phantom. In this video, I'll show you why a phantom voltage occurs and an easy way you can be sure that it isn't caused by some form of a fault or miswiring. The best part is that you can do this using an ordinary digital voltmeter. No special equipment needed. Let's get started. Let's say you're replacing an old outlet, have flipped the circuit breaker, and are making a quick check to make sure the circuit is off. But instead of seeing zero in the DVM, you see a voltage, not line voltage, but definitely not zero. Is it really there, or does it just appear to be there when you connect the DVM? Should you be concerned? You shouldn't be concerned. To understand why you measure a strange voltage somewhere between zero and line voltage, we need to take a brief, and I mean very brief, look at the theory behind something called a voltage divider. A voltage divider is a circuit consisting of a power source and two electrical components connected head to tail, also called a series connection. For simplicity, let's look at a direct current or DC circuit with two simple resistors. Part of the supply voltage appears across each resistor. The amount of the supply voltage appearing across R2 is proportional to the ratio of the value of R2 to the sum of R1 and R2. Here, for example, the value of R1 is much larger than the value of R2, and the ratio of R2 to the sum of the two resistances is 1 ohm divided by 9 plus 1 ohms, or 0.1, so the voltage across R2 is 1/10 of the supply voltage, or 1.2 volts. The actual values of R1 and R2 don't matter, just the ratio. If R1 is 90 ohms and R2 is 10 ohms, the exact same voltage appears across R2. In fact, if R1 is 90 million ohms and R2 is 10 million ohms, the exact same voltage of 1.2 still appears across R2. If the supply voltage is larger, say 120 volts, the voltage across R2 is still 1/10 of the supply voltage, and that would be, of course, 12 volts. The same thing occurs for AC as well as DC. In this circuit, the component values are typical of what will exist in the demonstration of phantom voltage. If the supply voltage is always 120, as it is for home power, and if R1 is always 133 million ohms, also called 133 megaohms, then the voltage across R2 will only depend on the size of the resistance R2. If R2 is 10 megaohms, then the voltage across R2 will be about 8.4 volts. And if it's very small, say just a few thousand ohms, the voltage across it will be nearly zero. In this voltage divider, just replace R1 with a capacitor and let R2 be the resistance of a digital voltmeter, and you will see the cause of the phantom voltage. C1 is capacitance, but it is not a component you wire into the power circuit. It's a capacitance that occurs naturally between bundled wires in home wiring. This capacitance acts in a complex manner, but for the purposes of this review, you can think of it as an AC resistor. In power wiring, an AC voltage divider is formed by the resistance of your digital voltmeter in series with the stray wiring capacitance. The math required to figure out how much of the 120 volt AC supply reaches the digital voltmeter is unfortunately somewhat ugly. Fortunately, we don't need to do that math to understand what's going on here. This diagram shows the stray capacitance between a live circuit and one that has been disconnected. The live circuit goes on to some outlets or overhead lights or appliances that are not shown. The gap between the unpowered circuit and the hot side of power represents the electrical equivalent of a circuit breaker switched off. Because the stray capacitance depends on exactly where the power cables are located, as well as how close and how long, it's nearly impossible to determine a value for stray capacitance. We know that it's there, but we never know the exact amount. Let's just pick a value for the stray capacitance and see where it leads us. In this example, we will use a stray capacitance of 20 trillionths of a farad, or 20 picofarads, PF for short. The property of a capacitance that can be thought of as like a resistor for AC is called reactance. 20 picofarads of stray capacitance has a capacitive reactance of 1 divided by 2 times pi times the frequency of 60 hertz times 20 picofarads, and that's just under 133 million ohms. 133 million ohms is much larger than the input resistance of a typical DVM of 10 million ohms, so only a fraction of the line voltage appears at the DVM. Remember the example of the DC voltage divider resistance ratio. In this voltage divider, reducing R2, which here is the effective resistance of the DVM, should cause the phantom voltage to go away or to be reduced to something very tiny. A simple way to do this is to connect something with a small resistance across the DVM. This will cause the equivalent of a DC voltage divider where the voltage across the meter is nearly zero. Let's see how to do this in the real world. First, you will need to collect some common parts. You will need 2 clip leads, a spare outlet, a 4 to 7 watt night light, preferably one that has an on-off switch. Start by connecting a couple of bare wires to the hot and neutral connections of the outlet. Plug the nightlight into the outlet. Connect the black DVM probe with a white clip lead to both the neutral on the outlet as well as the neutral on the circuit you are testing. Connect a black clip lead to the DVM red probe and also to hot on the outlet. With the nightlight switched off, make the phantom voltage measurement by touching the red probe and attached black clip lead to the hot wire on the circuit you are testing. You will see the phantom voltage on the DVM. Now switch the nightlight on and repeat. You will see the phantom voltage reduced to 0 or something very small. The voltage drops so low that the DVM measures 0, and that proves that the cause of the phantom voltage is stray capacitance, and you know it is not the result of miswiring or some other fault. Just to recap, you are seeing the effect of an AC voltage divider caused by stray capacitance. The capacitive reactance is much larger than the input resistance of the DVM, resulting in a portion of the line voltage being present and measured at the DVM. If you're wondering why the phantom voltage here is shown as 8 and 19.5 in the actual real-world measurement, the answer is that the former is a calculation based on an educated guess for the value of the stray capacitance as well as the input resistance of the DVM. The actual values are, of course, not exactly the same as this. That means that the measured voltage will not be exactly the same. Also remember that Adding the low resistance of the nightlight drops the divider circuit voltage to zero. That's how you can be sure the voltage is what they call a phantom. Caution: if the nightlight actually lights up, or if the DVM reading does not drop to zero when you switch the nightlight on, the voltage is not phantom, and it's caused by a wiring fault. One of the faults that can cause this is a loose neutral on a multi-wire branch circuit. If you suspect this is the case, treat the measured voltage as being potentially hazardous. If you are at all unsure, consult with a licensed electrician. I hope this video has helped to explain why phantom voltage measurements occur and the easy way to identify them with an ordinary DVM. So long until next time, and don't forget to push the subscribe button.